Welcome, dynamic students. This is the second of two curvilinear examples of particle kinematics. And we are going to again deploy Euler's first law to treat a body as a single point at its center of mass for the purpose of translational motion. So in this case, we have, again, our body treated as a particle at center of mass, moving in a curved path. So we have in this case, a vehicle that is starting out at 45 degrees, kind of down slope on this hill. And we're told that it starts at rest, and it starts at 45 degrees as an angle measured from the vertical. This line here is vertical, and this is the hill crest right here, even though it doesn't look like it due to my knobby drawing. The hill is circular in cross section, kind of an odd shape for a hill, but they do exist, and it's 1,000 feet radius. So this theta angle is actually decreasing. That's the convention we were given in the schematic. So as theta gets smaller, the car gets closer to the top of the hill, and it's traveling a certain path length defined as r theta because of our circular path. And we're given what's effectively a tangential acceleration of 6 feet per second squared, and that's another way of saying it is increasing its speed at a constant rate. Translational acceleration is 6 feet per second squared. So again, circular path, which is going to simplify our kinematics quite a bit. And we are asked the first time and the time and position when the car first leaves the surface due to excess speed. So it's going to stay on that circular path until it can't anymore, until we do not have any forces that will continue to satisfy the acceleration component that maintains the circular path. Literally, we're going to define it with our kinematics. And we're going to have to find some expression in our forces that define that point so that we can identify it mathematically. So we're just going to go back to our general steps for solving these dynamics problems. First, establish a coordinate system that makes sense. Second, draw an FBD. So we kind of have a choice of two coordinate systems. We could use a tangential and normal, where in the tangential direction is going to be basically the direction that the car is traveling on the road, and then normal would be on a radius back towards the hill. Or we could go with an r theta system, a polar system, which given the circular path is equivalent. I actually picked an r theta system to start with, and then ended up switching over to a tan normal to take better advantage of this tangential acceleration. So this will be a good example of showing how coordinate systems are sometimes equal to one another. So we're going to start in polar. So we picked our coordinate system, and now we have an FBD, so we're going to have to see what forces are acting on this car. So we've got the car, and here's our normal direction pointing down towards the center of the hill. My theta direction is effectively the tangential direction, theta, so I've got r pointing to the center of the hill and theta pointing in the direction the car is going. Forces. We got a normal force coming up from the surface, normal to the surface. Surprise, surprise. Get rid of that. So normal force. We have obviously weight acting vertically downward, so it's going to have a cosine theta component that opposes the normal force, and a sine theta component that's pointing opposite the direction of travel in the theta direction or tangential direction. Then what's making the thing move is, of course, the engine, which is generating torque and some complicated system in the car. But because we're considering this car a particle at the center of mass, we're just going to assume it's some motive force that's being delivered via some force on tire to road. So I'm calling this F tires to indicate whatever force is resulting from the engine moving the car forward. And so it's obviously acting in the theta direction. So tallying up forces, I have the force resultant in the radial direction is going to be mg cosine theta, which is the radial component of my weight, minus n, and that's going to equal the mass of the car times the total acceleration in the radial direction. So a sub r is acceleration radial. Tallying up in the theta direction, we have negative mg sine theta, because I've defined theta positive as going counterclockwise, and my mg sine theta is pointing, excuse me, theta is counterclockwise, mg sine theta is clockwise. So we've got a negative sign there, and then F tires is my positive force going in the theta direction. It's what's actually making it go forward. And so this is equal to m times a subscript theta. This is a theta. So there's my expressions for total force, and I've kind of snuck in a Newton's second law, reminding me to equate these to the mass times the magnitude of the acceleration in those directions. Okay, and I've put a few notes to myself, just kind of reminding myself of what's going on. And for instance, until the car flies up off the road, it's traveling a circular path, and if it's doing so, then my first time derivative in the r direction is 0, because r is not changing. So is the second time derivative. So those are all going to be equal to 0. So I may need to quick draw that relationship to simplify my kinematics. And then we'll pull in that next bullet statement in a minute. So I'm going to use polar coordinates to write an expression for the total acceleration for my car. And that'll help me identify the components that I'm going to equate to a sub r and a sub theta. So just recalling my expressions for polar coordinate acceleration, I've got r double dot, so second time derivative of the radius, minus r theta dot squared in the radial direction, plus r theta double dot. So this is this entire first term here. This is the tangential acceleration, by the way, plus 2 r dot theta dot, all of that pointed in the theta direction. So this whole collection of terms here is my a theta. So these are going to be what I equate to my force resultants. Okay, so let's simplify. Let's pull in our circular path simplifications. So r dot 0, this term goes away. Oop, not that whole term, just the second term. Let's try again. We have a tired hand. That term goes away, and that term goes away. So my a sub r just becomes negative r theta dot squared, and my a theta is just r theta double dot. So I'm going to insert those in my force resultant expressions, my Newton's second law. So in the theta direction, the direction of travel, the tangential direction along the road, I have F tire minus mg sine theta equals mass times this acceleration, r theta double dot. And I've reminded myself that if I'm on a circular path, I'm already starting to think, gosh, tan normal coordinate systems might just be more convenient. So I've reminded myself that r double dot is the same as s double dot if I were since I'm on a circular path. So this is s double dot is the tangential acceleration for a tan normal, because I was given that specifically, the value of k of 6 meters per second squared. Okay, so having said that, we can turn our attention to the normal direction. So we're going to relate this acceleration times the mass to our force expression. And so we end up with m times r theta dot squared, and reminding myself that this is equal to 1 over r s dot squared for a circular path. minus n. This ended up switching sign as I move over into my tan normal, which is why this negative sign didn't come down. That ends up washing out. So reminding myself again, you know, we've got r dot, r double dot 0. So with that simplification, we're effectively using a tangent normal. So I'm going to switch over from r theta dot and r theta double dot to s double dot and s dot from here on out. So I'm making the switch at this point, saying, okay, I'm switching coordinate systems and I'm using this relationship and this relationship. And of course 1 over r is 1 over 1,000 feet. Okay, now I'm going to invoke my what does it mean for the car to fly off the road? And this is truly the crux of the problem. When the car is just ready to lift off the pavement, we'll assume that it has actually come off the pavement by a differential radius bit, a dr. Because this dr is infinitely small, it's still on the circular path at that point, so all of our equations of motion apply, but because it is not actually in contact with the circular path at that point, there's no normal force. So if we look up in our r direction at our acceleration force Newton's second law expression, n goes away. And we're just left with mg cosine theta equaling mass times the radial acceleration that we get from our circular path kinetics, which could have either been r theta dot squared, or we could use m over the path radius times the tangential velocity s dot squared. Same. So I'm going to stick with tan normal because in this case the tangential direction is the road length. So if a highway engineer was out there saying, oh, where did the car go off the road, you could get a little pedometer, the little wheels that you use to measure distance along the road, and actually measure s. It's really hard to measure theta. You could maybe do it with some surveying equipment or some knowledge of the radius of the hill, but you can measure s directly. And so that was big in my decision to switch coordinate systems. They're equivalent. I could have used the data input to give me the same results, but if I wanted to verify this or relate this to real world conditions, S is directly related to length along the road. So that really made more sense given that this is a highway traffic kind of problem. So given the fact that N went away at point of liftoff at that instant, at the instant the car is ready to fly off, I just have mg cosine theta equaling the car mass divided by that 1,000 foot radius of the hill times the square of the car's tangential velocity. Okay, drat, how do I find that? Well, I'm given a constant value for the acceleration. So, and I know that's k. K is 6 feet per second squared. So I can integrate once and get kt, or 6 feet per second squared times t, plus some constant. At time equals 0, the velocity is 0 because I was told the car started from rest. So my s dot is just 6 feet per second squared times time. So that's a pretty nifty expression. So I can plop that in, and I'm going to call this equation A. So I have given, for any given acceleration, this is a label A, meaning equation A. So for any given acceleration, I can, and hill radius, I can relate the angle that it has traveled to the time, from the time we start accelerating. Okay, and I can add just a, to make my life easier, given the fact that I defined my starting point. We're going to go back to the schematic. We started at basically a theta of pi over 4 or 45 degrees, and we're going to, as time goes on, theta is going to decrease. So at some point we'll have chewed up that entire initial 45 degrees and be at theta equals 0. So we want to establish some kind of, as our distance down the road increases, that theta angle decreases, just because somebody kind of defined the problem oddly. Maybe they're doing an accident reconstruction and they wanted the starting point. So we can write an expression for distance down the road from the starting point in terms of theta, given the way the problem was defined, as just S equals R, which is at 1,000 feet. So, length equals R theta. And in this case, our theta that we've traveled is that pi over 4 minus the theta they've defined as the angle reference to the vertical. So that is just a way to relate the angle in our figure to the distance traveled. So if we put all that together and do our second, now we need an expression for S in terms of K, no problem. We do that by just integrating this again. So we integrate S dot again, so we get K over 2t squared with our starting position. And we're going to say in terms of S is our distance traveled. We started at 0 because we hadn't traveled any distance, so C2 goes to 0. So now I have an equation relating S and T in terms of K. I've got S in terms of theta, and I have theta in terms of K and T. So this is equations A, B, and C. And basically these are all going to be combined to give me a kind of a parametric expression for when and where I leave the highway in terms of K. So basically I have my equations of motion now. These A, B, and C basically give me the information I needed, and I could solve for them if I needed to. But we're gonna move forward and create a nice expression that we can input any acceleration with our K term. So I've skipped over a lot of the steps and just shown the result. This is something you would have to have already known you wanted to set up for. This is one example of a way you can combine those three equations so that they're ready to solve and put into a numerical solver. But if you did combine all of them, you could create this expression. And so that's just those three equations all combined with theta and S and T all substituted. Then if we take this expression, this time-dependent expression, and we call it Q, it's actually dimensionless. So if you look up, K is acceleration times time. So this is meters per second squared times time. So we got meters, 2R, R is in meters. So this is dimensionless, which is why we're able to operate on it with a cosine function. So if we call this Q, we can factor this expression a little bit and get Q times 2 times K over gravity. Then we can solve this equation numerically for Q, any Q, and Q is going to be in turn dependent on K, whichever acceleration we pick. So if we went ahead and solved this, we would find that for the K that we picked, Q is equal to 1.68. So that means the time that corresponds to liftoff is 23.7 seconds. We can input that back into one of our three ABC equations and equate that to an angle of negative 51.3 degrees. So if we go back to our schematic, we find that we've chewed into the 45 and now we're somewhere over here. So the car has gone up and it's on its way down and it goes flinging off. And if we wanted to find the distance traveled, which is something that we could go measure and verify, like if there's a lawsuit or some kind of investigation, we could equate that to 1,685 feet of travel from the starting point. And of course, with that, we can also find the velocity or the speed, S dot, at the time of interest, and know that the car was going 142 feet per second. So this might be used, for instance, to determine, was the road inherently unsafe or was somebody drunk and going too fast? So this is the kind of calculation and analysis you might do to solve that problem. This mathematical solution strategy of basically preparing something for input for numerical solution is beyond the scope of this class, but it is definitely would be an application that you would undertake if you took a numerical techniques class. This is absolutely the type of thing that you might want to write a program to do an iterative solution to. But you won't be expected to do that necessarily on a homework for a dynamics class unless you are doing a numerical solutions lab. It is definitely a natural follow-on. Because in this case, we had a fairly simple force balance, and we had a very clear n equals 0 time that defined our point of interest. And we ended up with 3 fairly simple equations, but getting at what we needed from those 3 required a little bit more sophisticated math. So that's how, just a glimpse ahead, even though this problem doesn't necessarily cover numerical solutions, it's showing you the power of them when your combination of force resultant and coordinate system acceleration expression gives you an equation of motion that you can't necessarily do something with in the form that you first have it. Nonetheless, it's the starting point that you would need. So let's go back lastly over key points. First thing, identifying what coordinate system. We could have used tan normal, or we could have used polar. We found that they were equivalent. We had to equate this language to a parameter that we would use as part of our kinematics. We identified this as tangential acceleration. And again, the crux was to kind of do some word problem interpretation of what does it mean in terms of force or acceleration, which is the only thing I can really determine. When does the car leave the road? So we were translating a visualizable scenario to what does that mean in terms of my forces? What does that mean in terms of my acceleration? We'll be doing that over and over again. And after that, FBD, express our acceleration in terms of our selected coordinate system, force resultants in an orthogonal direction to acceleration terms in that same direction for each direction, and then go through the math to get our equations of motion in a form that we can determine what we want. So that is it for this example. This is the last of our examples for particle kinetics. And so next topic we'll be diving into work energy and impulse momentum, which will be other ways that we can get equations of motions from forces in a little bit different scenarios, or from situations where a force balance might be hard to get. So stay tuned.